And welcome again. This time we're going to go over exercises for P4. Let's get going. First, we're just going to do some exercises with roots. I'm going to start off with exercise 22 on page 29. The last one in this set, D, I did create. It is not in the original problem. So this first problem, part A, in simplifying a root, generally what you want to do is factor it down and see if you can get any perfect squares or perfect cubes depending upon what kind of index you have on your roots. So on this 12 and 24, I'm going to take advantage that I know that 24 is actually a multiple of 12. That is 12 times 2. And so I have the 12 over here. Now remember from our properties of roots that you can split a root between a multiplication. So I'm going to write a separate square root for 12 and a separate square root for 2. A separate square root for this 12. Multiply a square root of 12 times a square root of 12. Well, it's just like squaring it. That's literally what it means if you multiply something by itself. And if you square a square root, cancel each other out, and you just end up with 12 root 2. Can't really simplify the 2 at all because it won't break down at all. It's not factorable. Let me get rid of this green line here. So, that's what we will write for our final answer on this part. This one, square root of 54 over square root 6, we can take advantage that we know if you have the same root, same kind of root on top and bottom, which we do, it's a square root, you can actually rewrite that as a single root. That means I can reduce this. That will be the square root of 9. And then, if you know 9 is a perfect square, you'll know you get 3. Or if you don't know that, and you just break it down and say 9 is 3 times 3. So that's the square root of 3 squared. Then we just end up with 3. Or the same rule as over here. If you square and square root something, it's just going to simplify each other away. This is actually very similar to that one, although I think there will be some differences. If it were a square root, 15 actually divides into 75, and we would have two 15s. But this is a cube root, and you need something cubed if it's going to come out. So let's see what we can get. 15 is 3 times 5. 75. Well, let me do a factoring tree. It doesn't really matter how I start. I'll start, though, with 3 times 25. And 25 is 5 times 5. Okay. So 75 is equal to, using all my end branches, 3 times 5 times 5. And I'm just going to combine this all into a single root. So now we have the cube root of, I have 2 3's, so that's 3 to the 2. And I have 3 5's, so 5 to the 3. Now, a cube root of 5 cubed, that'll just get me a 5 on the outside. Unfortunately, I'm going to have to leave the 3 squared on the inside, because I don't have enough 3's to bring one out. So, it'll just have to be cube root of 9 on the inside. D, part D here, just a very large number. So we're going to break it down. And I think on this one I'll actually get to show you guys an upshot of how to work these. So let's see, 960. Well, I think we can start off with 10 times 96. 10 is, of course, 2 and 5. 96. Well, it's divisible by 2. 2, because it's an even number. Divided by 2, you get 48. Oh, and I know a multiplication makes 48. 4 and 12. And 4 is a 2 and a 2. And 12 is a 3 and a 4. 4 is a 2 and a 2. Wow, that's a lot of 2s and 3s, and there's a 5. So let's see. Give myself a little arrow here. Now, that's a very diseased looking arrow. Fifth root. How many 2's do I have? 1, 2, 3, 4, 5, 6. I have 2 to the 6th. I have a single 5. And I have a single 3. If you're not confident that's the whole number, you're certainly welcome to multiply it all back together again. Should be 960 after you do. Now, as far as simplifying this, I won't be able to do anything with the 5 and the 3 because they both have a power of 1. But the 2 to the 6th, that has a 2 to the 5th inside of it. 2 to the 5th times 2 is the same thing as 2 to the 6th. So that means I can actually 5th root the 2 to the 5th and bring out a 2. I still have to leave the other 2 inside, so I have 2 times 5 times 3. And if you can't bring anything out, you may as well multiply them back together. So now I have the 2 5th root of, let's see, that would be 30. Notice an upshot here is that basically what we're doing is we're taking our index number here and bringing things out in this way. We take our index, we divide it into the exponent of each factor. 5 into 6 goes in one time. 6 divided by 5, 5 goes in one time. That's how many of the factor you can bring out. Since 5 went into 6 one time, I got to bring out 1, 2. The remainder of the division, because 6 divided by 5 is 1R1. The remainder of the division is how many of the factors stay inside. So I had a remainder of 1, I leave 1, 2 inside. Similarly, 5 divided into 1, 0 times with a remainder of 1, so I had to leave a 5 inside, couldn't take anything out. 5 went into 1, I missed 3. 5 went into an exponent of 1 0 times with a remainder of 1. I could bring out 0 3's, and I had to leave a 1 up here. Going back over here, 3 went into the 2 0 times with a remainder of 2. So I couldn't bring out any 3's, had to leave 2 inside. 3 went into 3 one time. So I got to bring out 1 5 and leave none inside because 3 went in evenly. You could also do something similar over here. If you didn't notice what I did here, and you just broke both numbers down. Well, 12 is 4 times 3, 2 times 2, and 24 is 4 times 6, 2 times 3, 2 times 2. So the roots would be, square root of 12 would be 2 squared times 3. And 24 would be 2 to the 3rd times 3. multiply them together, you get the square root of 2 to the 5th times 3 squared. And then we can play this game we were playing on this problem. You look at the index, which remember for a square root is 2. 2 divides into 5 twice, so that means I get to bring out 2 2's, and I get to bring out 1 3, and I have to leave in 2 divides into 5 twice with a remainder of 1. So that means I have to leave 1 2 inside, but 2 went into 2 evenly, so that means there's a remainder of 0. So there's no 3's left inside. So I end up with 4 times 3, which is 12, square root of 2. Same thing I had before. So this is a nice shortcutted method for doing these problems. You can certainly work them out longhand and try to find a pair of perfect squares, or find a number that's a perfect square in the middle like we did here. But the nice thing about this is it will always work. Eventually, you can factor numbers down to these prime factors, and then you can tell what you can bring out. It's a really nice method in that respect. The next problem we're going to look at is exercise 34 on page 29. This is a nice problem because it builds on what we were just doing before. We need to simplify this root, so we need to do the same thing we've been doing with the number, but the variables are arguably even a bit simpler because they're already in the exponential form, so we can already use the shortcut on them. But let's consider the number first. So if I'm going to break down 48, I think I've already done this one before. Oh well. 6 times 8, 4 and 2, 2 and 2, 2 and 3. So this becomes the 4th root of 1, 2, 3, 4. I have 4 2's, 2 to the 4th, 1 3, A to the 7th, and B to the 4th. This also will have one new piece of information as well. So 4 divides into 4 once, so I get to bring out a 2. It divides in evenly, so I don't need to leave any inside. So there's no 2's left. The 3, I can't bring any out. I've got to leave the 3 there. 4 divides into 7 once, so I get to bring out an A with a remainder of 3, so that means I have to leave 3 A's inside. 4 divides into 4 once, I get to bring out a B. Divides in evenly, so there's no B's left. Now, this is not the answer quite yet, because if you remember, the very last property of roots said if you take an even root of a variable, you're going to have to put in absolute value. Because, remember, the square root of -5 squared would be the square root of 25, and even roots only return the positive numbers. So, it's equivalent to just taking the absolute value of the inside. So whenever you pull a variable out, because you don't know what sign the variable has, you need to put it in absolute value. This is true for all even roots. Odd roots don't have to do anything. You could just leave it as AB with no absolute value. But even needs the absolute value. Here we're subtracting roots. If you're going to subtract root, it's a lot like subtracting like terms. You can only do it if you have this like roots. So for example, 3 root 2 minus 4 root 2, I could subtract it just like 3x minus 4x and get -1 root 2. But if they're different roots, 3 root 2 plus 4 root 3 No such luck. This is as exact a representation of this number as you can get, because these roots are infinite non-repeating decimals. I can't write a more exact form. If they wanted an approximation, like if the problem told you to round off, sure, I could add these in the calculator and get an approximation. But this is the only way to express this exact number. So what about something like this? Well, it doesn't look like we'll necessarily be able to get anything out of it, but let's simplify the roots and see if maybe they're like roots after we simplify. So square root of 125. Let's see if we get lucky. Take out a 5. 5 times 25. 25 is a perfect square, so I just square root that. I get 5 on the outside, 5 on the inside. 45. If I pull out a 5 from it, I get 5 times 9. And 9 is a perfect square. So square root of 9 is 3. 3 root 5. So yeah, we should be able to subtract these. 5 root 5 minus 3 root 5. I think that's all the time we'll have for this video. We'll finish up our look at the exercise in the next video. We'll do a few more problems with simplifying roots, and then we'll look at some rational exponent problems as well. Talk to you then.